Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 26th lecture of VLSI Interconnects course. We are in the third module where we are discussing additional effects in interconnects. So far in this module, we have discussed skin effect, which tells us that at high frequencies your resistance becomes a function of frequency. We have seen power dissipation and we discussed in detail how the overall power dissipation depends on the interconnect, especially the interconnect width. In the last two lectures, we were discussing heating and thermal effects. We saw why electrothermal modeling is required, and in the last lecture, we saw a method of doing this electrothermal modeling, which is compact thermal modeling. In this lecture, we will start with the final effect which we will discuss in this module, and that is electromigration. So, we will first understand what is electromigration, and then we will end this lecture with discussion on the reliability issue because of the electromigration. So, this lecture will be heavily based on images and figures which I have borrowed from various sources. So, to start with, I want to give you the references. So, this is not an exhaustive list of references on electromigration. There is a large body of literature available. However, these are the references from where I am borrowing some images and figures in this lecture. So, the predominant reference which I am referring is this Springer book on fundamentals of electromigration aware integrated circuit design. This book is authored by Lenig and Thel. And we will be referring to this book in this lecture and in the next lecture extensively. Then there is a very old paper by J.R. Black, which is from 1969. It is on electromigration, a brief survey and some recent results. This is the one of the previous papers on the reliability issues because of electromigration. And the method which is given by this author is now called as the Black's equation, which we will discuss. Then there are few more papers. So, there is one paper from Journal of Applied Physics, it is on void nucleation. Then there is a thesis from PhD thesis from University of California, Santa Barbara. You can access this thesis from here, and I have borrowed some images from this thesis as well. And then there is a paper in Journal of Electrochemical Society. So, it is on a stress migration and electromigration. So, here also we can there are some good figures where the electromigration is visible. You can find them here. So, let us get started. So, the first question before us is what is electromigration? So, let us see what is basically migration. I mean, the name itself suggests what it means. So, migration in solid state materials means the material is moving from under different forces. So, there can be chemical diffusion. So, this can lead to concentration gradient, and that may cause migration. Then, because of some thermal properties, because of thermal gradient, there can be migration in the solid materials, and that is called thermal migration. And similarly, there can be a mechanical stress which is applied at one end of your interconnect or other conductor, and because of that, again there will be migration of the metal ions, and that is called stress migration. In this lecture, we are focusing on electromigration. So, this is the migration of the metal ions under the action of electric field, and more specifically we are discussing about the solid state electromigration. So, electromigration is simply the migration or forced transport of material which consists of ions and atoms in a solid under the action of electrical current and electrical field. So, here is a figure which depicts this. So, this figure is taken from this book, Springer book on fundamentals of electromigration aware integrated circuit design. Here you can see that there is an anode and a cathode. So, when you apply an electric field, the electric field is in this direction towards the right, and under the action of electric field there are these electrons which are propagating from cathode to anode. So, they are propagating from right to left. Now, when they propagate, what happens is that these electrons would collide with this copper lattice ions. If this current density is large enough, then over time this momentum transfer from electron to this these metal ions is sufficient to shift or start shifting these ions. So, under the action of this electron, so this is called F wind. So, this is the force on metal ions resulting from momentum transfer from the conduction electron. So, under this action there would be this migration of copper. So, note that here the direction of metal migration is from lower potential to higher potential, that is in the direction of electron drift. So, if I have a conductor like this, I have a positive voltage applied from this side to right to left to right, the migration of your ions would be towards the left. Here is another schematic which explains the effects of this. So, because of this migration there can be a depletion in your conductor. So, here you can see that there is a void creation. So, this is called line depletion. There is this line is basically an interconnect, and there your metal has migrated. So, electrons were coming from here, and over time the metal has eroded. So, it is not that it is not an instantaneous process. So, it is not like there is a conductor, you have applied an electric field, electrons flow and suddenly this void is created. This happens gradually over time. This is very similar to the erosion process. So, there is a void creation here. Then this is called the via depletion, where there is this is the via which connects interconnects at two different levels, and here a void is created in this via, right. So, the consequence of this electromigration is that these voids are created. So, over time the metal gets eroded and you get a void of conductor. So, there is no conductor in a certain region, and this results in undesired open circuit. So, you would expect that circuit to be connected like this, but there is a void created here and then this becomes an open circuit. Now, when a metal is being eroded, it has to go somewhere. So, it will go somewhere downstream and then there it will get deposited. So, another consequence of this electromigration is formation of hillocks and whiskers, which results in unintended short circuit. So, there are two interconnects close by. In one place there is an erosion, so there might be the cross sectional area reduces, the temperature or the resistance increases, current density also increases in that region. On the other hand, that eroded metal goes downstream. Downstream means over the interconnect, and towards the other side of the interconnect it gets deposited, resulting in form sort of hills and whiskers. So, let us see some images. So, this image is again taken from this Springer book. Here you can see hillocks. So, this is the additional metal which got deposited over time. This is undesired. Here there are this is voids. So, you can see this void is there. So, this was a conductor, but over time metal has eroded from this. And so, in a zoomed in version you can see the grain boundaries, and why this grain boundaries and other things are important. that we will discuss towards the end of this lecture. Then this third figure shows your whiskers. So, it is not that always some hillocks sort of small structures are created. Sometimes these whiskers are also created, which results in unintended shorts between adjacent lines. So, this becomes a major issue, and this becomes a major this is becoming a major bottleneck in the reliability. There is another image here. So, this image is taken from that journal or in Electrochemical Society. So, here you can see this void and necking. So, this is that via, this is like the this is interconnect, this is the vertical via schematic which was shown, and here you can see that this has opened. So, this is resulting in an open circuit. Then there is another image. This image I have taken from this thesis from UC Santa Barbara. So, here you can see this electromigration. So, there are these sort of breakages in your line, and then here you can see hillock formation, and then this is so you can see hillock extrusion through a hole in the overlying glass layer causing a short. So, there are two adjacent conductors, and then a hillock is formed and it is shorting the adjacent conductor. So, this is a major issue in I mean in the long run, when this electromigration builds up over time, this becomes a very problematic issue. Now, as I had said that this electromigration does not happen immediately. So, it is not that you have a conductor, you have applied a current, electromigration happens maybe in 1 hour or 1 day, and then you have an open circuit or a short circuit. So, there is a lot more involved mechanism there. So, here I am referring to a paper in Journal of Applied Physics from 2009. The paper title is Dynamic Simulation of Void Nucleation During Electromigration in Narrow Integrated Circuit Interconnects. So, here you can see the lattice, here, and what happens is that randomly some vacancies are created. So, this generation of these vacancies would be a statistical phenomena, which will be decided by what is the temperature and what is the activation energy and other things. So, but this if you have these vacancies, these would be created and they alone will not cause an issue. But now what happens is that there is a current flowing in your interconnect, and there is a force of this electrons which are impinging on your lattice. So, under that action, over time some of these vacancies starts coalescing together. So, vacancies are not voids. However, when these vacancies starts coalescing together, they start becoming what is like tiny voids. Now, you can see that these tiny voids can move. So, here these you can see these arrows. So, you can see the current would be in this direction, and the electron flow would be in this direction. So, it will force suppose for example this ion to move from this point to this point. Similarly, this can move here, or even if there is this tiny void, you can see that this lattice point can then move on this direction. So, what will happen is that these tiny voids start behaving like a sort of pseudo particles which have their own identity, and then they start moving. So, these tiny voids may not be stable. However, over time they may start coalescing together and they can increase in size. So, for example, what can happen is there is a tiny void here, and then there is another void here, but then this small void can move in this direction, and then this is also moving in this direction, and then as they are moving they start coalescing together, and then now this is a bigger void which is created, right. So, now your voids can start behaving like particles. So, this is what is called void nucleation. So, you had vacancies coalesce to form small voids, and then these small voids are then moving in the direction opposite to the direction of electromigration, and then they start forming bigger and bigger chunks. So, here you can see how a void movement would be there. So, a lattice point would move from this point to this point, and then your void has actually essentially moved a small distance. So, this again this is not an instantaneous process, this happens gradually, very slowly over time. So, at certain point what happens is that when your voids become substantial size, then they become stable. So, when the voids are like tiny voids or vacancies, they are not stable. So, they come and go, and there is no they do not cause any major issue. However, so in this paper, this is the same paper from 2009 in Journal of Applied Physics. So, here there is a statement that when void radius is about 10 nanometers, it can hardly be broken up, and it remains as a relatively stable object during void nucleation process. So, once your void radius is now 10 nanometers or even more, then it is like an object which can move, and this is now stable. It is not it will not go away on its own. So, this results in your electromigration over time. So, if you want to have a complete picture of this electromigration, I will require solid state physics, and which is beyond the limits of this course. So, I am just referring to an equation which is on medium time to failure. What is median time to failure, we will discuss in a short while. But here you can see, if we consider all the physics, there is a very complicated equation which depends on various different parameters like void volume, V atom and other parameters. So, if you are interested in further reading, I would strongly recommend you to read this paper in Journal of Applied Physics, which is on void nucleation. However, as electronics engineers, we want a simple solution which is at a macroscopic level, and we want to have some quantification. So, right now, as I said that this electromigration does not happen instantaneously, it happens over time, but then how do I quantify it, right? Will my device fail, or will my interconnect fail in say 1 hour or 2 hours, or like what are the parameters on which the reliability of my interconnect will depend. So, to handle this quantification problem at a macroscopic level, we will look at what is median time to failure. So, a detailed physics based model will require the simulation of atomic flux divergence. So, this is discussed in the previous paper in Journal of Applied Physics, which I referred. However, a very simple and empirical equation is given. So, we define a median time to failure. So, it is not a fixed time, it's an empirical and statistical value which was given by J.R. Black. So, this was given in, he had wrote a series of papers in 1960s, late 1960s, and one of the paper is Electromigration, a brief survey and some recent results. So, this was published in IEEE Transactions on Electron Devices. So, in this paper he gives a very simple expression to get this median time to failure, and this is still in use for getting an empirical estimate of the reliability. So, let us discuss what are the factors that might affect my median time to failure. So, the first factor you can think about is the cross sectional area. So, if your cross sectional area is smaller, the interconnect is more likely to fail, because smaller voids will lead to your break in your circuit, right. What else? the current density. So if your current density is more, then your metal is more likely to erode and result in electromigration. So current density should be a factor. What else? Possibly temperature, because as we saw that the starting process is a statistical process. So also temperature, if we can intuitively guess that if the temperature is more, it might be because then there would be oscillations in your lattice, and then it will be more easier to knock out ion from its lattice position. So temperature should be a factor. What else? There is another term of activation energy. So what is activation energy? That we will discuss towards the end of this lecture. So the equation which Black gave is this simple equation. So MTF is median time to failure. This is equal to A divided by j to the power n. E is the exponent and EA is the activation energy divided by KT. So here A is the cross section dependent constant. So note that A is not the area, it is not the direct area, but this is, it depends, it is a constant which depends on the area. Then J is the average current density. It is not an instantaneous process. So on an average, what is the current density that would be there? So this is the average current density. EA, as I said, is the activation energy, T is the temperature, and K is the Boltzmann constant. So here from this equation we can make some inferences, right? So for example, if my cross sectional area is more, my device is less likely to fail. So my median, my device or interconnect is less likely to fail. So my median time to failure would be longer. So my A comes in the numerator of this equation. Now for current density, if my current density is more, then as we had argued that my device is more likely to fail because electromigration will be enhanced. So if your J is more, then your median time to failure will be less. So J comes in the numerator. Then EA is the activation energy that we will discuss, and T is the temperature. So if your temperature is more, in that case your exponent would be, the e to the power term, that term would be smaller, and your median time to failure would be smaller. So yeah, what is n? So n is a constant that is empirically determined. So this depends on what is the material, whether what is the dominant failure mode. So whether it's a surface, the electromigration is happening more at the surface, or is it happening in the bulk, or say the interior of your interconnect, it depends on that. So that is empirically found. So empirically in the reference papers by J.R. Blake, you can see that for aluminum they give n to be around 2, while for copper n is around 1.1 to 1.3, right. So one thing it should be clear is that this high median time to failure is desired. So more is the median time to failure, higher is this quantity, better is our interconnect or device, right. So now let us discuss the term of activation energy in this Black's equation. So activation energy is the bonding energy of the crystal metal lattice. So what it means is that basically you have this metal lattice, and then what is your bonding energy there, because that is the energy that would be required to knock out the atom or ion from that lattice position, right. So this depends on material, whether your material is aluminum or copper. It also depends on the location of the ion in the lattice. So you have a metal, so it's not a uniform or say an ideal sort of lattice, right. So where that atom is, that will decide your activation energy. So this is an image I had shown earlier, again from the same book. So here if we zoom into a region, we can see these grain boundaries, right. So if you look at this, here at this level, if I see, I can see that there is a metal, right. So, I would assume that there is metal lattice throughout like a monolith, but it is not the case. There are these grains, and each of this would have sort of a monolithic lattice, but then there are these boundaries. So, this becomes more complicated. So, if you have a interconnect like this, electrons are flowing from right to left here, shown by this red arrow. Electromigration can happen at 3 sites. The first site is A. So, A is like A is the grain boundary diffusion. So, this is at this boundaries here, right. So, grain boundaries are this, which I had shown earlier in this image. So, at these boundaries, if there is electromigration, so this is one site. The second site is bulk. So, inside the grain, in middle of that lattice, what is this B, and then there is this surface. So, this is at the edges of your interconnect. So, activation energy for all these 3 sites would be different. Now, if you have an interconnect like this, there can be these possible configurations for your how the metal is deposited. So, you can have a polycrystalline type of interconnect, where the grain boundaries would be dominating. So, these are like grain boundaries are very small, right? Your grains are very small. So, in this case, your grain boundary would dominate the electromigration. If you have something like this near bamboo, in this case both grain crystal lattice and grain boundaries are there. Then in case like this, where there is this bamboo sort of configuration, in this case grain boundaries are negligibly there. So, this crystal lattice would dominate your electromigration, and you will have to, or say the contribution of the activation energy for the lattice or inside the bulk would dominate. And then in the ideal case, you will have this monocrystalline thing, where there is crystal lattice, and these lattice defects if are there, then that will define. So, if we look at some values here, so for activation energy, again these values are taken from this book, which is Fundamentals of Electromigration Aware Integrated Circuit Design. So, here you can see for copper, which is mostly used now. So, you can see that bulk diffusion activation energy is 2.3, it is high. So, higher is the activation energy, it is better, and then grain boundary diffusion is this, and surface diffusion is this. So, for copper, your bulk has the highest activation energy, and the surface has the lowest. So, if you have this, so remember, like activation energy was coming as e to the power EA, right, in your median time to failure. So, higher is your activation energy, more will be your median time to failure, and the device will fail or device will work better at for a longer time. So, we want a higher activation energy. So, in that case, if we come back to this, what do you think would be the preferred lattice? So, we would want the activation, we would want a lattice where the activation energy is the highest, and if we look at, say for example for copper, we would want the bulk diffusion to dominate. So, we would want near bamboo or ideally monocrystalline type of lattice. So, let me summarize what we saw in this lecture. So, in this lecture we saw that metal ions migrate and erode under the action of this electron flow. This results in creation of voids, which leads to open circuits, and also hillocks and whiskers, which results in short circuit. For quantification, there is a very simple expression given, which is like Blake's equation for median time to failure. This is an empirical equation. And then we discuss the parameters that affect the median time to failure. In the next lecture, we will continue with our discussion on electromigration. We will see that why electromigration is becoming more important with scaling down of technology. So, why electromigration is actually becoming a bottleneck in your design. So, there is this book which is on electromigration aware IC design that specifically deals with this issue. And then we will also discuss some techniques for mitigation of electromigration. So that's all for today. We'll meet in the next lecture. Good day.